Okay, so welcome to this class. So basically, with chapter 4.1 to 3, we covered the main chunk of new results of about signed measures and complex measures. So 4.4 and 4.5 is applications. Very interesting ones. So 4.5 is just we have to finish up this stuff that the dual of LP is LQ. We will see that we need a random recording theory to work that out. But what we will do today is something called Lebesgue-Stieltjes integration. So this is some classical integral that you hear sometimes. For some reason, the book doesn't mention this name, but it appears occasionally when we read research articles, somebody is using that framework. But basically what it is, so this is an application only on the real line. Yeah. So before this idea of measure and measure theory got widespread, there was this alternative integral, I guess, Stieltjes, something to do with it, which was a way to define measures or integration against an arbitrary measure on the real line only, which is, for most applications, this is where we integrate. So they didn't have measures at the time, so they found a way of just having any increasing function with some restrictions on it. You could integrate another function f against that increasing function. And the way we know it now is like that increasing function, it defines a measure, and what the Lebesgue-Stieltjes integral is doing is just integrating against the corresponding measure. So what we have to do is we have to find a correlation between measures on the real line and functions on the real line. So the idea is simple. So we start with the other end. I mean, we have measures now. So I give you a measure and then I construct a function, and then we see how to revert the process. So here we deal exclusively with the Borel sigma algebra. So taking the closed interval from minus infinity up to x, if we have a measure nu, we can measure the size of this, and this gives us a number. So like that, we get a function of x. What properties does this function have? Well, it is right continuous. The limit as x goes to minus infinity is 0. And it is also a bounded function, yeah. So the measure is finite, and there's a maximum and a minimum value this can attain. So the natural question here is whether the converse is true, and the answer is actually no. We need something else from the function that I will come to in a short while. But first, an example. I wanted to take the Lebesgue measure, but I need a finite measure, so that's why I take the characteristic function of the interval between 0 and 1 times the Lebesgue measure, and we use this notation, the nu equals to yada yada lambda. You know by now what that means, even though it's not the most, it's a bit ugly notation in my opinion. Anyways, with this we get that f nu is equal to the function. I'll just paint it. So it's identically 0, then it starts to rise, and at 1, it becomes 1. So this is a continuous function, yeah? How do we get discontinuous functions? Well, let's take mu equals to the Dirac measure at 0. Then that mu is going to be equal to, I'll just paint it again. So here's the coordinate axis, and it comes here, jumps up, and then it stays 1. And note that it really takes the value 1. This is related to the fact, which is important, that we have a closed interval here. So as soon as when x becomes 0, 0 is included in the set, and therefore it jumps up here. This is where the right continuity is coming from, the fact that we have a closed endpoint here. So if we have, if we have a point, let me just explain that here. So if you have a point x, which is equal to limit
xk, where xk is coming from above, so you have x is less than x, xk plus 1 is less than xk, less than 1 for all k. Okay, so then this decreases. You have a bunch. Here's x, and then you have x1, x2, and so on. Right?
In this situation, we have that minus infinity up to x is equal to the infinite intersection of the intervals minus infinity up to x. K, right? And now we just use proposition 1, 2, 6, is it? Which says that, the limit of mu xk, that's mu minus infinity up to xk. The limit here, this can go inside with an infinite intersection, yada yada, and this is now mu of minus infinity to x, and that's equal to f mu of x. So that's where we see how we see that it's right continuous, not left continuous. So here we clearly get the jump discontinuity. Now, in both these cases, the function is actually increasing, right, or non-decreasing, to be more correct. And in that case, it is enough with these three. So if I have a function f, little f, which is right continuous, the limit goes to 0 as x goes to minus infinity, and it is bounded, then there exists a measure nu, so that f nu is the function. That was proven already in 1.3 when we were dealing with outer measures, but we skipped it then, and now we're going to come back to it. So I'll explain that today. But if we allow signed measures here, then the functions can go up and down a bit. And the point is that if the function go up and down too much, so it has a lot of variation, then it is possible that this process that to construct a corresponding measure breaks down. So, but before we get there, first a few notes. So, like here, you can see that f of f nu is continuous. That's the same as having mu of x equals to 0 for all x. So now we're back to this. I think I mentioned it in last lecture. This question is like, can we have singular measures such that this happens at all points, so that there's no point masses? If x gives a positive number, we call x a point mass. So do we have singular measures with point masses? And the answer is yes, because take the Cantor function. That's my last example. Right? We cannot paint it, but you remember it, right? You remove the middle, so here's 1, here's 0, and then you remove the middle third, you let it be a half there. Then you remove the middle third, you let it be 3/4 and a quarter, and then like that you get some sort of continuous function like this. So then it satisfies all these criterions here. So there exists a measure that says this theory, which I'm about to present. So let's call this Cantor function G. Right, so this measure nu, it has of course support between 0 and 1, and it's called the Cantor singular measure, I believe. But it's a peculiar measure then, because it gives mass to the interval between 0 and 1. It is singular with respect to Lebesgue measure, so it lives on a set of measure 0. Well, it lives on the Cantor set, right? We have mu of complement of the Cantor set equal to 0. Well, actually, that's probably not that obvious, but it's related to the fact that the function is constant here. So on each of these intervals, it gives measure 0 to those. But of course, we have to go through the construction of the measure before we can really see that. So now, just from an intuitive point of view, you have this. So this means that since this Cantor measure as measure, Cantor set as measure 0, this means that mu is singular. So right, so and it doesn't give any mass to any point because it's continuous. Yet it's non-trivial. So this is a curious example of a singular measure. Okay, so let's go back to 1.3 then and finish this. So theorem. Yeah, so if we add non-decreasing and bounded, then that is enough to define Borel measure. Borel is important here, such that we have this identity. Okay, how do we prove that? This is 1.3.10, by the way, in the book. So the idea is very much similar to what we did when we defined Lebesgue measure in 1.3, which is why Kohn put these results in 1.3. But from a presentation point of view, they don't really belong there, they belong here. But what did we do when we defined the Lebesgue measure? So we had some set A, I don't know exactly where it was, and then we covered it with intervals, so A1, B1, we took another interval, A2, B2, and like this, A3, B3. We kept on going until we had covered A, right? So we looked at coverings like this, so A subset union K goes from 1 to infinity, AK, BK, and then we said that the Lebesgue outer measure of A is gonna be infinite sum, well, the infimum of all infinite sums.
Marcus, are you speaking or?
Oh, I thought I muted myself. I'm recording the. So dk minus ak, yeah, for all possible such coverings. So here the idea is a bit similar. It's just that now, since we have this issue of right continuity, it's very important to know whether the right endpoint is inside or not. So in the most simple case, let's say A is actually the interval 0 to 1, then you can, instead of having an infinite covering, you can just say that, well, this this is your covering. So you do a union of one set, and you can think of all the other ones as being the empty set, technically. So what do we want then? We want, of course, we want mu of A to be equal to f
Marcus,
of 1 minus f of 0.
Yeah.
you only need the personal number on one page, right?
Yeah. Right, so it's pretty clear that if we're going to have.
Does it matter which page?
Okay, so if we want to have. If we want to have this, then it's pretty clear that we want to have also this difference here, right? Because, right, so mu of 0 to 1, where we're open here and closed here, is the same as mu. I mean, this interval you get by taking the difference of the interval from minus infinity to 1 closed with the closed one that ends at 0, right? So that's why, so then we just use if mu is a set, we can break this up. we get this one minus the measure of that one, and that will be then f of 1 minus f of 0. So that's how you see that we want this identity. So yeah, so how do we want to define this measure now? Well, since this thing with the endpoints is a bit picky, we now are going to require this instead, yeah? Because otherwise, this interval could be, yeah, I'm not sure if this is essential, but anyway, that's the way it's being done. And then here, we of course then want f of bk minus f of ak, and that gives us the measure nu star, right? So now you go back in your memory to this horrible theorem 1, 3, 4, or 6, something like that, that says that anytime you have an outer measure, it gives rise to a sigma algebra on which that outer measure becomes a measure. So we need to verify that this definition gives rise to a outer measure. Well, what's outer measure again? You need that if a subset, if A is smaller than B subset, then the corresponding outer measure should be smaller. And with this definition, that's pretty immediate. The other thing we need from outer measures is the following. Again, many of these things follow the same way, corresponding calculations we did for the Lebesgue measure, and indeed in the book they write it's a bit hand-waving as well. But if you think about it, so each AK is going to be covered. You know, you can take an infinite covering of your AKs. Now you get here you put another index J, right? And then you can call this K and that K, and now you have your AK like this. So you take a covering that gives you, so the outer measure here is an infimum. So if we have some epsilon, and you add a bit more, then you can take a complete covering. So that you almost get this number. And then you do that for all these sets, and you get the infinite covering of each set, but you have a countable amount of sets, so you just take all this countable set of countable sets that's again countable, and now you have yourself a covering of this kind. Did this get too messy? In my mind, it's very clear. Okay, let's do this. So you take epsilon bigger. This guy comes here plus epsilon divided to the power of k. So now you sum up here, you get this infinite sum plus an epsilon. So you have this infinite sum here plus epsilon is bigger than or equal to that double infinite sum, which dominates this guy, and then we get this inequality. Right. So okay, so then this defines an outer measure, and now we want to prove. Well, I mean, then the theorem 136, I believe it is, gives us that there exists a sigma algebra where it is a measure. And actually that sigma algebra is different. It depends completely on this function f. If the function f is the one that is 0 and then jumps up to 1, so that the measure we're trying to define here is the Dirac measure, then actually the sigma algebra is going to be the power set. All possible subsets are going to be fine. So it's not that we get naturally here the Borel sigma algebra. Even in the case of the Lebesgue measure, we didn't get Borel sigma algebra, we got something bigger, right? But the point is that all of them include Borel sigma algebras. We can be certain that we get a Borel measure out of this process, and that's all we're actually interested in. If the sigma algebra becomes bigger, we don't care. How do we check that the Borel sigma algebra is inside? Well, the Borel sigma algebra is the smallest one containing all open sets, and then we also prove that there are a few equivalent conditions for that. So the easiest one was to say that it's the sigma algebra containing all semi-axes, whether they're open or closed doesn't matter. Okay, so then we need to show that, let's take closed semi-axis is mu star measurable. What does that mean? So check that minus infinity up to some b is mu star measurable. Well, so we have to show that for all sets A, we have this identity. So the set we want to prove is measurable. It should split up any A in two pieces, what's inside the set and what's outside. So what's outside the complement is open interval from B to infinity. So we want this to split A in such a way that we have this addition formula working. Now, this is very easy to see, at least on an intuitive level, with this definition here, because, okay, maybe I should call this point X instead. So you have the real line, here's your X, and then your A is a bit all over the place, right? So here's A and a bit of A here. So if you want to measure this guy, you take A case and B case that cover this side here. If you want to measure that guy, you take A case and B case that cover this one, and then you play with the same idea here with this. You add a bit of epsilon so you can take concrete covering, so you get within epsilon of the measure, right? So now you have a covering on this side and a covering on that side. You just group them together, you have a covering over the whole thing, and you see that yeah, then you have sum up, you get a number which is bigger than or equal to this. And now you do it vice versa. Let's say you have now, you know, a covering that comes close to this number. So now your A case and your B case, the problem is that they can go. You can have an, you know, A here and a k here and a bk there, right? So they're on both sides. But then what you will do in such a way is you just artificially move your, you know, your bk is going to be this guy, and then you define this to be ak and a half, let's say, and you call this one bk and a half. And now you just split your interval in two pieces, and the sum, of course, cancels out when you consider this, and then you see that, all right, so now your covering of A, actually you can split it up, throw one side, well, half a bunch of the intervals to the left, the other bunch to the right, and now you have a covering of this guy and that guy, and then you get the inequality going the other way. So at the end of the day, you push both directions like this. Okay, so that's how we see that mu star gives rise to a Borel measure, which I'm going to call, or we're going to call mu. And what else is there to show? Sorry for my messy blackboard here, but we of course want to have this identity. And that one is almost immediate by the definition. It's just that I'm not allowed to put minus infinity here, right? In my covering, I should have finite numbers. So, but just take your x, let's say, let's just say that x, for simplicity, is positive. Otherwise, you just do similar argument, right? And then you write this minus infinity up to x as the union of the interval from 0 to x, union, and then here you do an infinite union and go from 1 to infinity, minus n minus n minus 1. Right? So this is now a covering of the this type that we consider here, and then what's the corresponding then sum like this? Well, it will become
f of x minus f of 0 plus f of 0 minus f of minus 1 plus f of minus 1 dot dot dot.
right. So you get a telescopic sum here. So everything cancels out. So this is f of x, well, except dim, minus, and then you do the limit as n goes to infinity of f minus n, because that's, if I do a finite sum here, this is what it's going to get. And then an infinite sum is just taking the limit of a finite sum, so then the limit sits here. And now we use this fact that, right? So here we just get f of x. Now, so this proves actually proves that the measure here is less than or equal to f of x. And intuitively, it cannot be the other way around, right? You cannot get a smaller number by doing some sort of smart. I mean, here I chopped up the interval from minus infinity to x in one way, but there's so many ways you could do this. But there's no smart way to kind of cheat this functional so that when you in the end sum up, you will get a smaller number than f of x. That's simply not possible, right? Intuitively. Technically, how we prove that, it is a bit, I'll just explain the details and then you can read it in the book. Sorry, I'll explain the idea and then you can read it in the book. So, sorry again. I had just established that this inequality is pretty obvious. And the reverse one we want to prove also is this one. And how would we do that? Well, first of all, it's hard to work with the interval that goes to minus infinity because we're going to use compactness at some point here in the argument. We want a finite interval. And of course, we want some epsilon that gives us a bit of room to play, right? So what we're going to do is we add a bit of epsilon to the side that we want to show is bigger than or equal to. And then I take instead here a finite closed in both endpoints interval, right? So if I prove this inequality, I can throw away first my epsilon because it's arbitrary and then y and x is fixed. Okay. And then I can take a limit, y going to infinity, and then, because mu is a measure, so if I do a limit as y goes to infinity on the outside, I'm still bigger than or equal to him, right? And the limit can go on the inside and turns into an infinite union because of proposition 125 that we use all the time, right? So it's enough to do this. And here it gets a bit, so, what the problem is, we have this, okay, let's say we have a covering now with AJs and BJs of this interval, just y and x, okay? But since there are infinitely many of them, this, could you take the first one here and then the next one here, and then in any gap you could have infinitely many of them. It's in a way to kind of fill this up so that when you do the infinite sum, you get less than the difference between this value and that value. Intuitively not, at least if it's finite. If we have a finite sum here, this cannot happen. Why? Because, well, somehow then you can order them. If you have finitely many, okay, if one is a subset of the other, then that's stupid. You just throw it away, right? So they're not subsets of each other. Then you need like to have the first one, and after that one comes the second one, which needs to have its left endpoint to the left of this one, right? So then it starts like this, and then it starts, it will go like this all the way up, and then you see that every time the left endpoint is to the left of the right endpoint of the previous one. In this sum here, the corresponding finite sum, you get a bit more, right? So when you sum up here, actually, sorry, we need, right? So we need to have him there. Yeah, so when you sum up, then each of these guys gives a positive contribution, so the total sum will be bigger than or equal to the value in the left endpoint minus the value in the right endpoint. Since this is non-decreasing, the value you have here is less than this one. The value you have here is bigger than that one, okay? So if we had a finite one, we'd be fine. But we don't have a finite one, and that's, you know, compact sets have this property that if you have a covering with open sets, you can always choose a finite subcovering. Yeah? I hope you have not bumped into this fact before. Otherwise, it's certainly here in the appendix somewhere, or we used it already earlier in the course, right? So open coverings of compact sets, you can always choose a finite subcovering. That's like the more appropriate definition of compactness in abstract topology. You know, the one we use normally, you know, on Rn is just closed and bounded, but that's okay. Anyways, that's equivalent with this property I just said. Now, the problem is that this is not an open covering, yeah? So if we have an infinite covering so that this sum is below this measure plus my epsilon, then of course I can move each bj just a little bit at the price of, and then get an open covering, right? And I can do it in such a way that I'm still respecting that this infinite sum, now it will be Tydel, is smaller than or equal to the measure here plus my epsilon. Now from this infinite, now I do the trick with the compactness, yada yada. So you see this gets a bit technical, then you have to somewhat specify, given your starting bj, how do you go a bit to the left to define your bj Tydel? You know, you can't go an equal amount to the left for all of them because you have an infinite sum. So if you sum up a small step infinitely many times to get infinity. So again, you have to play with something like epsilon divided by 2 to the power of j in this case, right? Yeah, so it gets a bit technical to read, but the idea is captured here in what we just. Okay, moving on. Okay, so why isn't this now extendable to the case when if f is no longer non-decreasing, but just allows to go up and down? Why isn't the corresponding statement true now that we have also signed measures? Well, you know, a signed measure, it has a finite variation. And it's clear if we allow the function to go up and down, it can go up and down a lot in a way that the variation would be infinite. So that's what we have to avoid. So we need some condition on the function that ensures that the corresponding measure gets, that the measure we construct from the similar process becomes of finite variation. And okay, so the condition is pretty, if you remember the condition for variation of the measure, it's not going to come as a huge surprise. So right, so the variation df is the supremum of sums of this type, where the endpoints are free and the amount of points are also free. So now if d arise from a measure mu, like we wanted to do, then this here is just modulus mu of the interval open in the left and close to the right, like this. Yeah? So we see that the supremum here actually becomes the variation of our measure nu. Well, at least we have that it's going to be less than or equal to. I guess when we do the variation, nu, there's no requirement to work only with this type of sets. We have any kind of subdivision of the real line, right? It doesn't need to be this type of intervals. But anyways, this inequality is always true. And we're going to see that actually you get equality here, right? So this is a natural condition. So here right, so how does this look like? You have your function here, f, right? It goes a lot up and down. So then, of course, you pick your t1 where it's down, and then your t2 when it's up, and then your t3 when it's down again. So like this, the supremum here measures the variation, yeah? So it's a very natural measure. So if this is finite, or very natural name, so if this is finite, then we say that the function is a bounded variation. Now, the theorem 2 of today, you can kind of guess it, right? So if we have some function f whose limit as x goes to minus infinity is 0, it's right continuous and finite variation, then there exists a Borel measure, a signed Borel measure nu, such that we have this identity. And the proof is a bit more refined like this. So if you add this set here, then right, and you have that a is less than or equal to t0 or t1 in my case, and then tn should be less than or equal to b. All right, so what's the proof of this one? Instead of somehow kind of repeating the whole machinery, what we want is we want to write f like this. Yeah, if both here are non-decreasing, then what I previously showed will give rise to two measures, nu plus and nu minus, and then I will just define my nu as the difference here, so we kind of get the Jordan decomposition of our signed measure for free. So how do I achieve this? Well, it's actually, if you think about it, so so if x is here, this contains all the ups and downs. Right, so if I either add or subtract f, then I'm going to get something which is non-decreasing, right? Because this one has all the variations, so he cannot vary enough to make this go down. Okay, and basically what you need to understand is that the variation of f, if you have done this decomposition here in a minimalistic way, maybe my notation is bad. This is not a positive and negative part, but this is somehow smallest function where f is increasing, and this is the smallest function where it's decreasing, and then you take the difference, so you get f. If you've done this in a minimalistic way, then your bf here is going to be the sum of those two guys. Okay? So what we want then is define our b, so f plus, you do this plus him, and you divide by 2. Okay? So you prove that this is non-decreasing. And now this gives rise to a measure nu plus. And then, of course, f minus is going to be vf minus infinity to x minus f. Okay? And that gives rise to my v minus or nu minus. And now you do this one minus that one. Now these two cancel out. Oh, I have to divide here by 2. And this one and that one reinforce each other. So the difference of these two guys becomes my f. And yeah, there you go. That's the idea of the proof. The details are in the book. Okay, so can we, well, let's take a look at an example here. So if f, is C1, yeah, so to get a feeling for this, we start with a simple example. You should always do that in mathematics. To get a feeling for something, you make additional assumptions so that it becomes easy to work with. Okay, so then you know that f of x, or let's take f of b, if I subtract an f of a here, this is integral from a to b, f prime x dx, right? Or maybe better notation, just write f prime d lambda. This is the fundamental theorem of analysis. So if f now has the property that the limit as a goes to minus infinity is 0, then with a bit of dominated convergence theorem and yada yada, we can write this, right? And then you see that, well, if f is C1 and also bounded variation, the corresponding measure that we get is given by the new integration of the derivative against lambda. For such a measure, we know, okay, I haven't technically proven that yet, but it's in the book. So the variation of f is going to be equal to the variation of nu, and for such measures, this is equal to the integral of the modulus of the derivative, right? So we need this to be finite, and then the use of the dominated convergence theorem here when we take the limit is justified. Okay, so the measure nu that we get is just the integration against the derivative of f. And why didn't we just start with that? Well, as we saw from this Cantor function, there are cases where they don't arise like this, right? Because the Cantor function, the derivative is 0 almost everywhere. So this, now we come to this beautiful generalization of the fundamental theorem of calculus, because now comes the question, okay, if we change notation here a bit, so I call this big F, yeah, then I just call him small f. Okay, so small f is the derivative of big F now. So if f is C1, then this is fine, everything works. But you can clearly define many functions big F by integrating some L1 function here, but then the function you get here is not C1 any longer, right? So the question is, can we extend fundamental theorem of calculus so that you allow sort of derivatives that are not continuous, just any L1 function? And the answer is yes. But to do that, we have to somehow get rid of the singular measures. So apparently having finite variation is not enough for getting rid of the singular measure. So what sort of condition could we put so that we don't have a singular measure, meaning that we want an absolutely continuous measure, right? Because the absolutely continuous ones, by the Radon-Nikodym theorem, they can be written precisely like this. So we want a condition on big F for that. Now, what's the condition for absolute continuity? It is that if you have a set whose Lebesgue measure is 0, then the corresponding mu should have also measure 0. Well, it turns out for the function that doesn't translate naturally to functions. So we have to come up with something a bit more tricky that involves an epsilon and a delta. So basically, okay, if we had a measure nu like this, then an equivalent definition to absolute continuity would be to say like this: for all epsilon bigger than 0, there exists a delta bigger than 0, such that okay, let's say we have this condition. For every epsilon, there exists a delta such that yada yada holds. Now take an E whose measure is 0. Then for every epsilon, we can pick a delta, then this E will satisfy this inequality because this guy is 0. And then we see that mu of E is less than epsilon. Epsilon is arbitrary. So it means that if this is 0, this will be 0. right? So this is a more clumsy way of doing absolute continuity for measures. But the good thing is that this is easier to lift to the function setting. So
definition. F is called absolutely continuous if all epsilon bigger than 0, there exists a delta bigger than 0, such that
right, so if I take a bunch of open intervals, n is of course free here, then some of the Lebesgue measure of that is this, right? So if that's less than delta, we want also the nu to be less than epsilon, but nu is not defined yet, so instead we look at the differences here. Because yeah, if we have our nu, then basically this will be, well, the measure of the, well, right? So yeah, and here we'd like to have the variation, of course. So then this becomes like a definition of the variation. And whether this guy is included or not, it turns out it doesn't matter. Because well, for measures of this type, it doesn't matter if you include the right endpoint. So this definition works and it's motivated by thinking like this. Okay, so that's a bit of a cumbersome definition. Not so easy to test in practice, but at least with this definition, we get this beautiful correspondence. F is absolutely continuous. If and only if the measure nu it gives rise to is absolutely continuous. And basically the proof is not hard, it's basically just looking at what I said. So this is almost the definition of the variation of nu. Here, of course, I wanted the big F, my idiot. Yeah, so I skipped the details. The details are in the book. So with this, we get this beautiful extension of the fundamental theorem of analysis, basically saying as follows: if F is absolutely continuous and has finite variation, then I don't want to add the assumption that the limit as x goes to minus infinity is 0. So let's just take some finite a. So let's introduce L1 compact. So it's L1 on any compact set, so any finite length interval, not necessarily L1 on the full thing. Yes, this is what we get. Beautiful. No? Is this the final version of fundamental theorem of analysis? Fortunately not, because once we reach here, it again raises new questions. So, okay, this is not differentiable as a function of b then. We just replace b by x, and then b can also be the variable. So then the question is, as a function of b, can we differentiate this? No, because then we can. If f is a continuous function, then we know that the derivative becomes, f at the point b. But then somehow this is unsatisfactory. Is it true that we could? Okay. So what's an example here? Take characteristic function of 0 to infinity, then that's my little f, then my big F becomes this guy, right? And here it's not differentiable at that point. So anytime you have a jump discontinuity in little f, you get a discontinuity in the derivative here of your big F, so you get points where it's not differentiable. Question is this guy differentiable almost everywhere? And is that derivative that you get then equal to F almost everywhere? And the answer is yes to both questions, but to do that, we actually need yet another full machinery of difficult stuff called Vitali coverings. And that's done when we look at differentiation and in general differentiation of measures in chapter 6. So that's coming up ahead, but at least we established this beautiful correspondence here today. I didn't say how to prove this, but I mean, if you have some f, and the limit as a goes, so if the limit as a goes to minus infinity exists, then we get this by just summing up what we already have. If we don't have that, so let's say you have some function that's finite variation and it's absolutely continuous, but it keeps going up and down, then just take your point, okay, here's the axis, take a here and say that, well, at this point A, I'm going to have a jump discontinuity and then just you replace it with 0. And now you have a function which is, and then you do the same here at some number B. You just define it to be constant beyond that point. Now you have a function that's bounded variation. So you apply, and also absolutely continuous, except that maybe here where you have a jump discontinuity, right? Yeah, so then the rest is just some blah, blah, blah. Then you get your function f on the interval from a to b, and then you take a sequence of a to b, go to minus infinity, plus infinity, and that's how you get your f, which is L1 compact, compact subsets, but not necessarily L1 full thing. Nice. So I still haven't said what Lebesgue-Stieltjes integrals are, although I put that as the title of today's class. So
point here is correct.
So the book doesn't mention this, but Stieltjes, I'm not very certain on the history here, but it's called Lebesgue-Stieltjes integrals. I guess Stieltjes probably was before Lebesgue. I don't know, but anyway, so some of these old guys, including those two, figured out a way of defining the integral from a to b of some function, let's say h, integrated against this non-decreasing guy f. And as you can imagine, it's a bit, it's something like the Riemann integral. You do your partitions, but instead of multiplying with, the length of an interval, you multiply with, right, so when you do your Riemann integral, you have your partitioning, and then right, you have your function like this is your h, and then you have these guys, right? From above and from below. Yeah, and they have some height, m1, m2, and here you have a1, no, b0, b1, and so on, right? And when you do your Riemann integral, you're interested in sums mj, t, j minus t, j minus 1, right? So now, if you want to define this object, you just do the same, but here you put your f of tj minus f of tj minus 1. Okay, and blah, blah, blah. That's how you get your integral. But we don't need to do all of that, because now it follows that with this machinery of measures and the correspondence, that each f gives rise to some measure nu, that this integral just becomes the integral of h against this measure nu that is given by, maybe I should have big F, I shouldn't change notation all the time. Well, I guess that's too late now, but anyway. Okay, so this F gives rise to him. So we can as well take this as a definition instead of fiddling with some boring new version of the integral. But anyway, it can be done, and then you prove that these two concepts leads to the same thing. So that's what Lebesgue-Stieltjes integral is about. In particular, if you do f of x equal to x, then the corresponding integral actually becomes just, even the notation fits, right? So the integration against this function x becomes the Riemann integral. So beautiful, nice. But why bother about this? I mean, is there any point to this except for historical reasons now that we have this way of thinking about it? Actually, there is a point, because some things are much easier to visualize and remember once you get used to thinking about integrals in this way. So, for example, you remember this partial integration formula, f of b times
g of b minus f of a times g of a is equal to the integral from a to b f prime times g dx plus.
boring formula to remember, right? But it turns out that it can be extended. There's a version of it for measures, and now it gets very ugly. Now I have to somehow, for each function f, if the derivative doesn't exist, I have to associate with it a measure. But with this Lebesgue-Stieltjes notation, I know that, so the measure given by integrating the back here against the derivative, that's the one that arises from this function f. So with the Lebesgue-Stieltjes notation, we can do this. Yes, and now this formula extends to any, it became much more beautiful, and you can somehow intuitively feel it more, and it extends now to any absolutely continuous functions f and g, right, with finite variation. So you don't need the restriction that the derivative needs to exist. It can be further extended also to functions of just finite variation, but then we have to worry about this discrepancy between, you have to jump discontinuities. And actually they have done that in 5.3 in the applications that we skipped when we were there last time. So if you look at proposition 5.3.3, you see how the formula would have looked in the full generality and without using this Lebesgue-Stieltjes notation. And as you can see, it gets much more ugly and much harder to then, of course, also remember. Okay, so to wrap up this lecture, I'm going to give you a really beautiful example of how to apply these things in a concrete situation. So a classical, nice field of mathematics is distribution of zeros for entire functions. That's complex analytic functions. Analytic functions in the complex plane, right? That's what it is. And so they have zeros, but you know that in every compact set, an analytic function with multiplicity only has a finite amount of zeros. So you want to know some of the correlation between how fast the function grows, in some sense, as c, the complex variable, goes to infinity, and how many zeros there are. Okay, so this is a huge field. So let's let lambda be the set of all zeros. Okay, there are infinitely many of them. Let's assume that. Okay, and then as I said, any complex function has a finite amount of zeros in a compact set. So we can just assume we're interested in how many there are, like at infinity, or how fast they accumulate. So if you take the unit disk, we can just assume that there are no zeros whatsoever there. There's a way of dividing out zeros without changing the function too much. So, okay. And the analytic function here is actually going to be invisible in my example. Right, so now we can introduce a function which just counts the amount of zeros within a certain radius. So set n of r equals to the amount, this number means the amount of points lambda k, such that modulus lambda k is less than or equal to r. So how is n going to look like? Well, it's going to be 0 up until 1, we know that, and then when the first 0 comes, it's going to jump up. Here's 1, right? And it's going to be right continuous because I have less than or equal to. And then, so that's the modulus. The first lambda k, then comes another one, then maybe there are 2 lambda k's which have the same modulus, and then it will jump up to 4 immediately, and so on, yeah? So it grows like this. So how many zeros are there is connected to how fast does this function grow to infinity. Can we say something about it? Well, let's see. So one way to talk about how many or how fast the zeros grow would be to consider the sum of all the zeros below a certain r. And since, you know, what should I sum up here? Well, if I just put a 1, then I get back my function n, right? But I want something that does not go to infinity, so I'm going to divide here with the modulus of lambda k. Okay, and maybe hopefully this could be like a finite number. Or, and anyways, how fast this grows will give us some idea of also the distribution of zeros here, right? So let's say we're just interested in this quantity. So now, so this is a function n, right? So this gives rise to, it's right continuous, it's increasing, non-decreasing. So it gives rise to some measure. What sort of measure does it give rise to? Well, clearly, here the first time it jumps, you get the Dirac measure for the modulus of the lambda, which has the lowest modulus. So in general, if you sum up from them all, this is the measure that this function n gives rise to, okay? So with this Lebesgue-Stieltjes notation, well, I mean, this sum here can now be considered as the integral from 1 to r, close, and point here, important, of 1 over x times this measure mu. Yeah, but that's now using this Lebesgue-Stieltjes notation, I'm not going to write that. So I'm going to think of this as integrating 1 over x times the function n. Okay, what's the point with all this? Well, now we can do the partial integration formula on this, and it becomes much easier to figure out what is the correct expression with this notation now. So what is the value in the endpoints? I have n of r, and this guy is divided by r, minus n of 1 divided with then 1. And then I have minus, and now the roles have to be switched, right? So I have one function n and one function which is 1 over x. So I'm working only on the positive real axis here, so you have to do some modifications to the theory I told you upstairs. But from a principal point of view, nothing changes, yeah, and it's easy to guess now what should be the correct formula, and indeed it is true, and that's an exercise to figure out the details, that we can flip here. And now, instead, I integrate the function n of x against the function 1 over x. Now, what should that mean? Well, first of all, this guy doesn't exist because he's 0 here, that's the value 1. So I just get this n of r divided by r. And then, while integrating against the function, which is c1, we just figured out that that's integrating actually against the derivative with this classical Lebesgue-Riemann integration what you want. So what's the derivative of 1 over x? Well, it's minus 1 over x squared. So here I get minus becomes plus. There's a minus there as well. So 1 up to r. And now it actually doesn't matter if the endpoint is included or not. So let me use this more sloppy notation. N of x divided by x squared dx. Okay. So this already tells. So let's say we know. Okay, I should have posted it like that. But let's start with this. Let's say for some reason you know that this sum, as r goes to infinity, you can put infinity here and it's finite. If you know that this is finite, what can you say then about how fast this function n of r grows? Now I already kind of hinted to the answer. But if I hadn't done these computations and I had asked you that question, you would be like, well, I have no clue. And that's the correct answer. It's very hard to see a connection between this sum here being finite and something about how fast he goes to infinity. But thanks to these computations, look at this. If this here is less than infinity, then I already know that this is a finite, well, it's bounded by that number because here's something positive, right? So I don't need to, you can just throw him away and get an inequality. So you immediately see two conclusions. First of all, n is big order r. N of r is big order r, right? Bounded by some constant times r, this function. And maybe less interesting, but anyways, let's register it. The sum, the integral from n from 1 to infinity, n of x divided by x squared dx is also a finite number, right? Because this is positive, so if you let the r go to infinity, then you get a finite number here. So this is information, right? In fact, if this had been precisely order r, but not little order r, then you would get an integral here like 1 over x, right? And that's, it's not less than infinity. So maybe we can even use this to push it a bit more. Well, that is also true. So if you think about it, so the integral from r to infinity, 1 over x squared dx, that's equal to 1 over r, right? So if I write, well, let me flip order here. So divided by r, 1 over r. But now I write n of r, and I can write also here n of r. Okay, now I have this formula. Just that, well, okay, now it starts to look like this guy, and actually n is increasing. So this is less than or equal to integral from r to infinity n of x divided by x squared dx. And yes. So if this number here, if this is a finite integral, then the monotone convergence theorem tells us that the limit as r goes to infinity of this tail here is 0. But then this limit is 0. The monotone convergence theorem, MCT, implies that the limit n of r divided by r is equal to 0 as r goes to infinity, or n of r is little order r. I should have specified that already up there. Usually when we speak of order, or the variable goes to 0, but you can also speak of although the variable goes to infinity. So n of r grows slower than r as r goes to infinity, in the sense that this limit is 0. Yeah, a lot of information obtained from just assuming that this object here is finite, and this trick with these formulas here. So, which are much easier to see or to work with when you have this Lebesgue-Stieltjes way of thinking of integration. So, yeah, I'll close this class here for today. So thank you, and see you next time.